All right, so welcome to my talk titled "In Understanding Astronomical Filters." This presentation is an abridged version of my four-part video series of the same name. You can find that on YouTube. Today, we will cover what filters are and how they work, how to select and use filters. We'll talk a bit about special filters and then some more advanced topics such as what happens when you use them with high-speed optics, or why do we get halos around stars using filters? If you want to see the full-length versions of these videos, you can find them if you search on the channel name Abbey Road Observatory on YouTube. So without further ado, let's get on with part one. What are they? So the general appearance of a typical filter is shown at the bottom of the screen. Typically, there's a machined aluminum housing within which a flat piece of glass fits. This whole assembly screws on the end of your eyepiece or the nose piece of your camera, depending on what you're using. If you are using a filter wheel with your astrophotography rig, then there may not even be an aluminum housing, just a flat piece of glass. The key is in what that piece of glass does. A filter's purpose is to make darker in the view the wavelengths of light that you don't want to see. Doing this helps you to see the desired parts of the scene more clearly due to the increased contrast, but filters do not make the object brighter. It only makes what you don't want to see darker. This is achieved using two different methods. One is absorption of the wavelengths that you don't want to see, and the other is reflection. Thus, there are mainly two types of filters. The first type are most commonly referred to as planetary filters, but are, in essence, color filters, commonly identified using the Raton numbering system. These filters are all absorption type. They block light by absorbing it. The other type of filter goes by several names, including deep sky, nebula, or light pollution. Regardless of the name, though, these are all interference type filters. They block light by reflecting it away. There are also special purpose filters that use a combination of absorption and reflection, which I will discuss later in part 3. This is a graphical representation of an absorption filter. These filters consist of dye-infused glass or a colored gel that is sandwiched between two thin layers of glass. The molecules in the dye are selected to absorb some wavelengths, but not others. The result is a filter that can selectively block light, but in a rather imprecise way, in broad bands with gently sloping cutoffs. Interference-type filters are rather different than absorption filters. They are made by adding tens to hundreds of extremely thin alternating layers on a glass substrate. Each layer is made from a material with a different refractive index. At each boundary between layers, light partly reflects and partly refracts. By choosing the thickness of these layers carefully, it is possible to have all the reflections and refractions of undesired wavelengths out of phase with each other, so they cancel themselves out, allowing only the desired wavelengths through. For the next couple of slides, I will describe some commonly used terminology, the first being the idea of a spectrum. A spectrum is a quantitative visual way of presenting how well a filter transmits light at different wavelengths. The example spectrum shown here is the typical format for presenting filter spectra, with wavelength on the horizontal axis and percent transmission on the vertical axis. Spectrum plots allow for easy comparison between filters, and provide information on how the filter will perform in different situations. The next item I'd like to go over is some basic filter nomenclature. This filter spectrum plot is for something called a low-pass filter. All the light at wavelengths below the cutoff are passed, and all those above are blocked. The opposite of this filter is a high pass, where all the wavelengths above the cutoff are passed and those below are blocked. If we combine these two spectra together, we get a band pass filter. In this case, a wide or broad band pass. The spectrum type is defined by its center wavelength and its band width, also referred to as its full width half maximum. The full width half maximum is literally the wavelength width from one side of the band to the other, with the cutoff wavelengths placed where the transmission value is half the band's maximum. Bandpass filters can come in any width, from wide to narrow. It also is possible to have more than one passband. This, for example, is a multi-narrowband spectrum, which I will talk more about in Part 2. The idea of multiple bands can be taken to the extreme. With filters that have so many passbands, they are sometimes referred to as comb or notch filters due to the shape of their spectrum. I refer to these simply as multi-broadband. The last term to discuss is luminous transmissivity, or %LT. It is essentially a measure of generally how dark a filter is. On average, what percentage of light is getting through. It is calculated based on the specific sensor the filter is to be used with. So a filter will have a different %LT value if used with the human eye versus with a camera. For perfectly clear glass, the %LT value is 100%. %LT is a useful metric when choosing a filter, as I will explain shortly. So that concludes part 1. Now we can either take questions between sections or at the end. What do we prefer?
Do we want to take a poll of the room on that? What's the preference for questions now versus later? Later is the consensus from the room.
All right, we will charge ahead then. So let's start with an example of how filters can be used to enhance planetary observing. Specifically, let's consider this typical Earth-bound view of Mars. By adding either a red, a green, or a blue filter, it is possible to enhance the contrast of certain features. Recall that filters are used to darken some features but not others. This is accomplished when planetary observing, primarily using absorption-type color filters. The filter spectra plotted here are for the most common color filters that you will be able to find available for amateur astronomy. Remembering our filter nomenclature from Part 1, blue and green filters are all broad band pass filters. Yellow, orange, and red filters are all high-pass filters. Pinks, purples, and browns are all combinations of high-pass and band-pass filters. There is quite a long list shown here of different filter colors. Do we need to have all of them in our accessory bag? Which filters are best to use is unfortunately very subjective. There is a lot of trial and error required, and in the end, it comes down to personal preference. If you like, you can read astronomy books or find online resources that will tell you the best filter to use for observing the planets. The end result will be a list, as long as your arm, of the filters you simply must have in your kit. The alternative is to take the advice of the poor schmuck who actually took the time to test all of these combinations for himself. Personally, I have found most filters do very little to improve the view. The list of filters that actually do something significant is short. On Mars or Jupiter, a magenta filter like a Raton number 47 or a number 30 does a good job of enhancing contrast. A red filter on the Moon or Mars also works well to sharpen the image and improve contrast. A light tan or orange filter like a Raton number 81 or a number 85 is also beneficial in enhancing details in the bands on Jupiter and Saturn. If you often observe a nearly full moon or Venus, you may also want to use a variable polarizer or neutral density filter to cut the brightness. If you are lazy like me and just want one all-purpose filter for planetary observing, you may want to consider a special type filter called a moon and sky glow, or more generically, a neodymium filter, which I will talk about a bit more in part 3. One important thing to remember about color filters is that filters block light, so your view will be darker. Dark filters, so those with a low value of %LT, may require a large aperture scope to be used effectively. Based on my own experience and the anecdotes of other observers, I have constructed this graph relating color filter %LT to minimum telescope aperture. As an example, assume you are observing using a 4-inch aperture scope. From the graph, the suggestion is to only use color filters with %LT values of 30% or higher. Based on this table of %LT values, that would mean a number 80A blue or a number 38A dark blue would be too dark to use if your vision is mostly dark adapted, but probably okay if looking at a bright object like the moon or Venus. For those of you who are imaging solar system objects, contrast, color, etc., can all be controlled after the fact during post-processing. So a color filter is not needed. The main concern when imaging is the seeing, the unsteadiness in the view resulting from turbulence in our planet's atmosphere. At a minimum, you should use a UV IR cut filter to sharpen your view, or try filters passing red or infrared only, as seeing has less of an impact at long wavelengths. Again, a good all-purpose filter for imaging exists. The moon and sky glow I mentioned earlier does a good job of cutting UV IR and enhancing contrast. Moving on now to deep sky observing, let's explore what sort of benefits can be realized when using a filter. This is an image of the Flame and Horsehead nebulae captured from my backyard during an electronically assisted astronomy session, but not using a filter. My sky conditions, by the way, are a solid Bortle 9+. Compare that with the same view after a multi-narrowband filter has been added. Same length exposure, just adding the filter. Clearly, there is an advantage to using a filter on emission nebulae. As another example, consider this hand sketch I made while visually observing M42 from my urban backyard using a 4-inch refractor. Without a filter, all I could make out was a smudge of nebulosity around the trapezium stars. Adding a medium broadband filter improved the contrast and allowed a bit more of the features around the perimeter to be visible. Moving to a narrowband oxygen 3 filter resulted in a large improvement in the amount of faint structure that I could see. And finally, The multi-narrowband filter gave the best view, with subtle differences in the brightness of the features now visible. How deep sky filters work has to do entirely with their spectra. They are designed to pass only the desired wavelengths of light, in this case, of an emission nebulae. Those desirable wavelengths correspond to emissions from different gases, such as hydrogen, oxygen, nitrogen, and sulfur. For galaxy emissions, infrared is also an emission of interest. Deep sky filters block light pollution to varying degrees depending on the filter category, of which there are 4. Broadband filters have one large passband around hydrogen beta and oxygen 3. They are meant for visual use, so they often do not have a passband for hydrogen alpha. For convenience, I have subdivided broadband filters into 4 subcategories based on their bandwidth: extra wide, wide, medium, and narrow. Narrowband filters have a single passband located at one of the desirable wavelengths for nebula emissions. They are available in a range of bandwidths, with filters in the 10 to 20 nanometer wide range being suitable for visual or imaging use, and those narrower than 10 nanometers being suitable for imaging only. Multi-broadband filters have combinations of multiple bands of various widths. They are designed to block discrete wavelengths corresponding to different sources of light pollution. They provide the best white balance of all the deep sky filters, but their overall light pollution reduction capability is poor. LED lighting that has become progressively more popular in the past few years makes these filters even less effective. The final category is multi-narrowband. These are a relatively new category of filter, being available only for the last 10 years or so. Multi-narrowband filters have 2 or more narrow passbands centered on desirable nebula emissions. And by narrow, I mean less than 20 nanometers wide. You will often see these filters referred to as dual, tri, or quad band filters, depending on the number of nebula emission bands they capture. These filters maximize the amount of light pollution that is blocked, and have become especially popular amongst one-shot color camera owners. The question you are now probably all wondering about is, which filter is best? To answer that question, we need to explore the light pollution problem a bit more. Light pollution is all the light entering your telescope from sources located between us and the deep sky object. The most obvious source of light pollution comes from man-made outdoor lighting, some of which illuminates our view directly, and some illuminates the sky by scattering off dust and moisture in the atmosphere. There is also a naturally occurring component of light pollution generally referred to as sky glow. This light is emitted by atoms in the Earth's upper atmosphere that were energized by the sun's UV rays during the day. The final naturally occurring source of light pollution is, of course, the moon. It acts like a big mirror, reflecting the sun's rays back at us. As suggested by these component spectra, shown on the right, light pollution consists of both broadband and narrowband emissions. To understand the implications of this on our filter choices, we next have to look at the spectra of deep sky objects. Deep sky objects can be grouped into 2 categories based on the nature of the light they give off. The first category is broad spectrum objects. This includes galaxies, star clusters, and reflection nebulae. Basically, anything that we can see because of light emitted from stars. The fact that these objects have broad spectrums makes them very difficult to pick out from light pollution using a filter. The second category of objects are narrowband emitters. These include objects like H2 regions, star-forming nebulae, planetary nebulae, and supernova remnants. Any object that we can see because of light given off by excited gases like hydrogen or oxygen. Because these objects emit at very specific wavelengths, they are much easier to separate from light pollution using a filter. The last thing to consider before choosing your deep sky filter is telescope aperture. Remembering for earlier, filters block light, resulting in a darker view. This means that the percent LT of a filter will limit the aperture of scope you will be able to use it with visually. This plot provides a general recommendation for how dark a filter you can use for different sized scopes. At the top, I have marked off the ranges of percent LT that are common for the different categories of deep sky filter. So, for example, if you wanted to use a typical medium broadband filter, so that's the yellow bar there, with a 4-inch refractor, you would probably be okay. Trying to use a narrowband visual filter, so that's the darker green band, is probably pushing your luck with a 4-inch refractor. For imaging or electronically assisted astronomy, there is no such limit on scope size because you can simply compensate with more exposure time. This does, however, mean that you will need progressively better mount tracking the narrower the filter is you want to use. There is one final thing to note in regards to aperture. The impact of a filter on broad spectrum objects is much worse than for narrowband objects because the filter is blocking light from the object as well as the light pollution. At last, we have come to where the rubber hits the road. What is the best deep sky filter to use? If you are observing or imaging a narrowband object, the best filter to use is the narrowest bandpass filter your aperture or mount tracking will handle, regardless of how much light pollution you have, be it Bortle 2 or Bortle 9. If you are observing broad spectrum objects from a dark sky, don't use any filters for visual observing. If imaging, an IR cut filter or a multi-broadband can help contrast, but the improvement is small. If visually observing broad spectrum objects from a light polluted location, well, I'm afraid there isn't a filter that can help. If using a camera, however, a wide to medium broadband filter that passes infrared works best on one-shot color cameras. An even better contrast can be achieved using an infrared high-pass filter on a monochrome camera, although long exposure times will result. I have one additional thing to note about trying to image in infrared using a refractor. Most ED doublets and APO triplets are okay, but achromats do not do well focusing IR light along with the visible spectrum, resulting in fuzzy bloated stars. The same is true for many camera lenses. For these types of optics, you can see a large improvement in your images by using an IR cut filter. Besides the beneficial effects mentioned already, filters have a number of other effects on your observing or imaging. The first thing to note is that filters change the scene's white balance. Broadband filters add a magenta hue, O3 a green hue, H beta cyan, H alpha red, and IR pass a brownish red color. Some filters are better than others for white balance. For example, multi-broadband filters give a good color balanced image. For those of you who are doing EAA or imaging, post-processing may or may not be able to completely correct for the hue added to the scene by the filter. Another effect to note is that filters will change your focus slightly because of refraction across the thickness of the glass substrate. Enough that if you change from one filter to another, there is a good chance you will need to refocus. That is why many users like to purchase all their filters from the same manufacturer, so the glass is all the same thickness, permitting filter changes without refocusing. Finally, filters add two more surfaces in your optical train to have reflections off of, although anti-reflective coatings can help. Filter surfaces can also collect dirt, dust, or dew, so yet another thing to keep clean. The final aspect of choosing a filter to talk about is cost. It is tempting to save money and go with a cheaper option, but quality often suffers. Cheap filters are prone to reflections, halos, delamination, poor machining, optical distortion, poor optical transmission, and various other issues. There are a lot of filter manufacturers available today, perhaps too many. I have put them into 5 groups, ranging from premium filters, which are super expensive, to high quality, which have proven themselves to provide a consistently high-performing product, followed by good value, which are brands that are significantly cheaper than other brands but still deliver a high level of performance, and discount brands, which will do the job but tend to have lower performance. The 5th group of filter manufacturers are brands that you should avoid, as in my experience, their filters often fall short of their published performance. Astronomic, Antlia, and Optilong are my favorite brands in the high quality category. And amongst the good value manufacturers, I have had good success recently with Altair and SV Bonney. That brings us to the end of part 2. Moving on now to part 3, special filters. The first special type of filter to discuss is the ultraviolet infrared or UV-IR blocking filter. This filter type is intended for imaging only, since the human eye is not sensitive to these wavelengths of light. UV-IR blocking filters are used to pass only the visible spectrum, resulting in sharper and better focused images. This is so because many lenses and telescopes, as I mentioned earlier, are designed to properly focus only visible light, not UV and IR as well. Included in this group are so-called color correction or CC filters, which modify the spectral response of a camera sensor to be more like the human eye. The blue and magenta curves on the plot at right are both spectra for commonly used color correction filters. All commercially available digital cameras have some sort of CC filter installed. Unlike the other special filters that I will discuss below, UV-IR cut filters are very common and are readily available from many different retailers. A word of warning, however, that many of the available filters have poor response to the important wavelength of hydrogen alpha at 656 nanometers. So before you buy one, you should confirm what sort of response the filter provides. The next type of special filter to discuss is neutral density. This is a purely absorption type filter whose purpose is to attenuate the brightness of the object you are observing uniformly across all wavelengths. They are available in a variety of optical densities, meaning you can usually find the right filter for your application. The percent LT of a neutral density filter can be calculated from its optical density using the following equation. So, for example, a neutral density filter with an OD of 0.6 has a percent LT of 10 to the minus 0.6 times 100 equaling 25%. Another option for reducing the brightness of what you are observing is to use a variable polarizing filter. This filter is in fact two linear polarizing filters stacked on top of each other. As you rotate one filter relative to the other, you change how dark the filter combination is. Many observers prefer the flexibility of a variable polarizing filter over having a selection of ND filters with varying optical density. The next category of special filters to consider is that for planetary observing. As discussed in Part 1 and 2, astronomers commonly use color filters in an attempt to darken planet surface features and improve contrast. By applying interference coating technology to this problem, unique filters that accentuate multiple surface features simultaneously can be created, something a simple absorption type filter doesn't normally do. There are a number of planetary contrast enhancement filters available commercially, most of which are designed specifically for improving views of Mars. In my experience, these filters work, but just like with the use of color filters, the improvement is very subjective. Of the filters I've tried, none stand out as being a whole lot better than a simple color filter. I also have a general caution regarding the transmissivity of these filters. Some of them cut a very large percentage of the incoming light, making them unsuitable for smaller aperture telescopes. For example, the Orion Mars filter I personally found too dark for use with my 8-inch SCT. For those interested in imaging the planets, there is another special filter category that may be of interest: UV and IR pass. These filters take advantage of the fact that cameras have a wider spectral response than our eyes. This opens up an opportunity to image the planets using wavelengths of light we can't normally see. Infrared pass filters are very popular because of their ability to steady seeing conditions to provide sharper images. They can also be used to view features that are not visible in other wavelengths of light. I especially like to use an IR pass filter when imaging the moon, as I discuss in more detail in my video Seeing Beyond the Visible, if you're interested to check it out. UV bandpass filters are also popular for those interested in imaging structure in the clouds of Venus, or for imaging methane distributions in the clouds of the gas and ice giants. There are few vendors of UV bandpass filters, so they tend to be a bit more expensive. Somewhat related to special planetary filters are special color filters, of which there are two main groups: those meant for studying star brightness, and those used for color imaging with a monochrome camera. The first group are meant for those pursuing the study of star brightness called photometry. By observing stars using a selection of very specific bandpass filters and comparing the observations to calibration stars, one can determine the star's spectral class, temperature, and other useful properties. The most commonly used filter set for photometry is the UBVRI or Johnson set, the letters denoting the color of each filter in the set, so ultraviolet, blue, visual band, which is centered on green, red, and infrared. The UBVRI filters are all absorption type, but have very specific formulas so that photometry measurements taken by different astronomers using different brands of filters can be directly compared with each other. A more modern version of these filters are modeled after those used for the Sloan Digital Sky Survey, which are interference type. The need to have these filters carefully calibrated tends to make them a lot more expensive than normal color filters. The other application of special color filters is for astrophotography, specifically generating full color images using a monochrome camera. To achieve this, the astrophotographer divides the visual band up into 3 color channels, red, green, and blue, using carefully designed filter sets. The most desirable of these filter sets are interference type, so as to have high transmission values and sharp cutoffs with minimal overlap between filters. Bandwidths for the filters are selected to give complete coverage of the visual band, but also keep sub-exposure times similar between the 3 filters. There are a number of advantages to creating a full-color image in this way, as opposed to using a one-shot color camera. Light pollution is reduced. You take full advantage of the camera's resolution, and with no bare matrix, the monochrome sensor is more sensitive. These color filter sets are often sold along with a UV-IR cut filter, also called a luminance or L filter. Since they are all interference type filters, they tend to be more expensive than typical color filters. The next category of special filters is that meant for the correction of chromatic aberration in achromatic refractors. This aberration is observed in the form of a violet fringe around the edge of bright objects. The solution most commonly used is to add a filter that removes the unfocused violet-blue end of the spectrum. These filters commonly go by the name of fringe killer or minus violet. I have personally used the Bader fringe killer, that's the red line on the transmittant graph on the right, with my 80mm achromatic refractor, and I can confirm that the filter does what the name suggests. If you are looking for a cheaper solution to chromatic aberration, try using a yellow Raton number 8 filter. That's the yellow curve on this plot. It should help. Using a chromatic aberration correction filter, you should be prepared for the fact that your view will have a yellow color cast. Depending on your specific telescope, the increase in sharpness and contrast may be worth the false color. A category of special filter that I briefly mentioned in part 2 is the neodymium filter. The concept of using neodymium, a rare earth element, to infuse the glass in an astronomical filter is somewhat serendipitous. The resulting glass media has multiple passbands in the visible spectrum, and by some strange happenstance, the end result is a surprising increase in perceived contrast. These filters are available from a number of manufacturers, and they provide good contrast improvement with high overall transmittance. I personally use the Moon and Sky Glow filter whenever I observe planets. There are a number of variations on the basic neodymium-infused glass filter that tailor the filter for different applications. Some have interference coatings to provide UV-IR blocking, making them good for imaging. Some have additional blocking in the violet-blue end of the spectrum to improve the performance of achromatic refractors. All in all, they are a curious family of filters that are worth having a closer look at. Note, however, that even though some manufacturers say that these filters provide light pollution reduction, the amount by which they do so is negligible. The last special filter category to discuss are those meant for solar observing and imaging. The main purpose of these filters is to reduce the sun's brightness to a safe level for observation. They are also used to isolate very specific wavelengths of light to highlight different aspects of the sun's various layers. There are many, many different types of solar filter. So many that it is a topic best left for their own presentation. If you want to learn more about solar observing and imaging accessories, you can check out my video, Supersizing Your Solar Setup. So that completes part 3. We're really moving along here. So now on to the last topic, advanced filter topics. It may be obvious, or perhaps not, that it is possible to stack 2 or more filters together to achieve a compound result. The thing to remember, however, is that the result of stacking filters will always be a net darker filter. The resulting spectrum does not equal the sum of the individual spectra, it equals their product. Take, for example, stacking together 2 color filters, a Raton number 38 blue and a number 56 green. The spectra for these 2 filters are shown on this plot on the right, the line color corresponding to the filter color. The result of stacking these 2 filters is a significantly darker, effective filter with a passband centered around the color cyan. Sometimes filter stacking can actually be useful, as it allows us to achieve desired performance when a suitable filter does not otherwise already exist. For example, adding a UV IR cut filter to one's setup is relatively commonplace. Doing this can block unfocused UV IR to improve image sharpness. Another common use of filter stacking is for narrowband solar observing and imaging. By stacking 2 less expensive bandpass filters, one can effectively get an extremely narrowband filter. The next advanced topic is that of narrowband filters and fast optics. If you can recall from part 1, an interference type filter's bandpass is defined by the thickness of its layers. Thus, if you change the thickness of the layers, you change the filter's passband. It so happens that if light is directed through the filter on an angle, you effectively increase the thickness of all the layers. This graph here on the right is the measured spectra of the OPT radian triad filter, plotted around the filter's hydrogen alpha passband. I measured this filter's spectra over a range of filter angles relative to the light path using my benchtop spectrometer. You can see how the passband shifts down and left as the angle of the light passing through the filter increases. By using a filter on faster and faster optics, we are effectively increasing the angle at which light is passing through the filter. This results in the filter center wavelength and peak transmissivity shifting down. And correspondingly, the desired band transmission goes down. This effect is made worse for filters with small full-width half maximums, although the full-width half maximum value itself is not strongly affected by band shift. The amount by which a filter's passband shifts down with angle is dependent on filter coating properties, most notably a parameter called the effective refractive index. The next advanced filter topic is regarding the ongoing race to produce the best multi-narrowband filter. These filters first arrived on the market around 2011 and have become very popular with one-shot color imagers and EAA enthusiasts since around 2018. The reason for their popularity is they are able to greatly improve the contrast and signal-to-noise ratio of emission nebulae. Presently, there are 27 different models of multi-narrowband filter available commercially. I have plotted them here in terms of the width of their oxygen 3 and hydrogen alpha bands. The dot color denotes the cost of each filter. An asterisk next to the filter name indicates those I have personally tested, which is most of them. The popularity of the multi-narrowband filter has motivated filter OEMs to work on developing the ultimate filter. What is considered ultimate has two possible definitions. Filters that give reasonably good performance at the most affordable price, like those I have circled here on the plot, and filters that give the overall best performance. The latest contender to enter the multi-narrowband filter arms race is SV Bonney. Their SV220 3nm filter delivers practically the same performance as other brands like Optolong or Antlia, but at a significantly lower price. The next advanced filter topic to discuss is star halos. This image of the Flame and Horsehead Nebula should be familiar to many people, including the nice juicy halo around the star Alnitak. The presence of halos in astro images is a topic of much debate, with many astro imagers of the opinion that they'd spend more money if it meant they'd get a filter that did not produce halos. To answer the question, what filter properties cause halos in the first place, I performed what is perhaps my most elaborate set of experiments to date. To gain as broad an understanding of the problem as possible, I assembled a library of 45 different filter samples from my collection, exposing them to all sorts of tests. If you would like to see all my test results, you are welcome to download the 40-page summary report from ResearchGate, a link for which is provided below. For the sake of brevity, though, I will share only my final conclusions today. The first of which is that the primary cause of filter-induced halos is intra-filter reflections, so reflections taking place within the filter itself. Finding number 2 is that halo angular size depends only on the filter glass thickness and the optic's F ratio. Thinner glass and longer focal lengths produce smaller halos. Distance to the sensor has no impact on the appearance of the halo. Finding number 3 is that for stars of the same visual magnitude, those with either very hot or very cool surface temperature tend to produce more prominent halos than stars with moderate temperatures. Finding number 4 is that filter off-band blocking is the primary characteristic affecting halo generation, with better blocking resulting in less prominent halos. In my testing, I found that filters with off-band blocking better than OD4 had little or no halos. The final finding is that anti-reflective coatings on a filter help reduce halos, but they are not as important as off-band blocking. The final advanced filter topic to cover is how narrow a filter is too narrow. As I have already discussed, there are some advantages to having a narrower full width half maximum, including increased object contrast and increased signal to noise ratio. There are also numerous disadvantages, such as increased subexposure time, increased mount tracking, increased difficulty with discussing and registration of images, increased sensitivity to F ratio, and perhaps most importantly, increased cost. All of this raised a question in my mind. Is there an optimum full width half maximum? Do the benefits at some point get outweighed by the detriments when the bandwidth is too narrow? To answer this question, I took a deeper look at hydrogen alpha filters, performing a series of analyses and tests on filters ranging in bandwidth from 100 down to 0.1 nanometers. What I discovered from my analysis and testing is the following. For filter full width half maximum down to zero point 0.1 nanometers, there does not appear to be a limit on contrast increase with decreasing bandwidth. For the situation of heavy light pollution and modern low noise camera sensors, there does not appear to be a limit on signal to noise ratio increase either. Under lower light pollution levels, or when using a noisier sensor, the signal to noise ratio benefit flattens out for full width half maximums below about 5 nanometers. These conclusions are related specifically to what is theoretically possible. Also important to consider are the practical limitations of using a progressively narrower bandwidth. The first thing to consider is f-ratio sensitivity. As I already discussed earlier, sensitivity to band shift increases with decreasing bandwidth. Full width half maximum values below 2 nanometers are probably not practical for the general amateur astronomer market for this reason. Filter bandwidth also affects subexposure time. As full width half maximum decreases, so does the amount of light passing through the filter. To maintain the optimum usage of camera dynamic range requires subexposure time to be increased in conjunction with decreasing bandwidth. For a 10 nanometer H-alpha filter, a subexposure approximately 50 times that of no filter is required. And for a 1 nanometer filter, about 500 times. Subexposures on the order of a minute or two are manageable with the equipment available nowadays, but subexposures 10 times that length are not practical. The final aspect to consider is cost. To be able to fabricate filters with full width half maximum values below 2 nanometers that are useful to amateur astronomy would be difficult and expensive. Based on the price versus bandwidth relationship of existing commercially available filters, the price expected for a premium quality 2-inch diameter 1 nanometer wide filter should be in the $1,500 to $2,000 range. And a 0.1 nanometer filter should be between $2,500 and $3,500. Perhaps a few super serious amateur astronomers would be willing to pay that much for a filter, but I imagine most people would say that is too expensive. Well, that is it. Thank you everyone for listening. If anybody has any questions, I'd be happy to answer them.
See if we have some questions here. Questions? There you go. Steve.
First of all, great talk. I found myself wanting to ask a question that was subsequently answered by a later part. So deferring questions at the end was a good thing. I'm wondering, since I have a really fast scope of like f3.5, and I've traditionally used narrowband filters like an L Ultimate at 3 nanometers. Do you have, and you know, I understand the problems of trying to combine those two. Do you have any experience or comments on, I guess, some of the manufacturers or have new filters out that cater to faster scopes by trying to shift the band pass accordingly, you know, try to compensate for the steep light cone?
Yeah, so if you were to, I've tested, as I've alluded to, many different filters, including all of the 3 nanometer filters that are currently on the market, of which there are 5 models, 5 brands. And part of that testing includes testing them at different angles, and from that data, plotting out the sensitivity to F ratio. And most of the 3 nanometer filters are going to give you good performance down to around F3. If you go below that, though, the drop off is quite sudden and steep. So say you were trying to use it with an f2.8 lens, a camera lens, you would only be getting like 30 or 40% transmission. The filter still, that's the funny thing, because the bandwidth is not affected by band shift, you're still getting a decent amount of blockage of light pollution, but your signal is greatly impeded. So you would have to compensate by increasing your sub-exposure more than you would think you would need to. Um, so I have heard of people using uh, conventional narrowband filters on like Ross's and Hyperstars, and they get good results. Kind of clueless to the fact that their exposure time is way longer than it could be if they used a pre-shifted filter, where, as you say, the manufacturer knows how much the band is going to shift down when it's used at f2, and so they construct the filter with the band shifted to the right, pre-shifted to the right, so that once it's band shifted in service, it's right where you want it to be. There are a few companies that make pre-shifted filters. Antlia is one example. They've got quite a selection of pre-shifted filters. Optolong has their, I don't know if you can still buy, they had an F2 Extreme for sale for a while. And the first company to really think about that whole idea of pre-shifting was IDIS with their MBZ filter, which had a pre-shifted version. Does that answer your
Yeah, no,
question?
that was great. I was trying to do a quick calculation earlier in the thing, and I said, well, my light cone at f3.5 is like 8 degrees, and you had presented a graph that was showing the shifts, as a function of the incident light angle, and that's caused the concern. But I understand what you just said, so I'm optimistic that this might work. Thank you.
So yeah, the plot that I showed you earlier, when I collect my data, it's parallel rays of light, and the whole filter is at an angle. Where in reality, when it's used in a telescope, it's sort of an area average. So the light going through the center of the optics are perpendicular, and then as you go out to the edge of your aperture, the light cone is getting steeper and steeper. So it's really only the light at the outside edge of your objective that is causing the band shift. So it's when I do the amalgamated plots in my test reports, it's an area averaged calculation over the full aperture of the scope. So it's not as bad as what was portrayed in the plot in the presentation. So that might have been a little misleading.
Next question.
Sure.
Well, first, I thought I knew a lot about filters. Turns out I don't know anything.
Well, now you know a lot more, don't you?
One question, as to what Dave was talking about, do flats partially correct for that shift?
No, no. So
No?
it's it's a kind of difficult to think about. It's not like having vignetting,
Okay,
where you have light intensity falling off as you get away from the center of the frame. This has to do with how much of the object signal is getting to the sensor from different parts of your objective. It's weird to think about, but light coming through the edge of your aperture is actually covering the whole surface of your sensor. It's kind of you have to go to your optics textbook to think about it. But if I have a bunch of parallel rays entering your objective, um, they illuminate the entire sensor area.
okay,
So the filter causing band shift at the edge of the aperture, it's more like putting an aperture mask on your scope. That's the effective, what you would observe in the end effect of your images. It's more like adding an aperture mask
okay.
to your scope, not
Second,
vignetting.
second question is, I'd never really considered sky glow and moon filters. Would they serve as a good luminance?
Possibly, yes.
Okay.
They have, so depending on the brand, the Beta Planetarium brand has a UV IR cut built in. That's why I use it when I do planetary imaging. Other brands do not. Um, but it has a relatively high percent LT. Um, so it could be worth trying. Yeah.
Question?
Which way is the microphone?
Just anywhere.
Anyway, hi. Quick question. What is considered a fast telescope, specifically refractor for astrophotography? Because that's different than for regular cameras. So.
That's a sliding scale, really.
So would would
so-
f4.9 be considered fast? Not
Yes.
so fast? Yeah. Okay.
Yeah.
Thanks.
Not super fast, but it's relatively fast. And f4.9, you would not need to worry about band shift. It's when you get into the f3 range and below is when it's a problem.
So I have a question. So very early on in the in part one, you had mentioned that you had showed Mars with three different color filters: red, green, and blue,
Mhm.
and they all seem to have a significantly impact on Mars. But then a few slides later, you said if you're going to shoot Mars or look at Mars, I'm sorry, this is visual observing, you should use a red filter. I guess I was confused as to why you wouldn't use the green and the blue, because that looked pretty cool.
Well, that was a simulation, and because I was applying a filter on a computer image that's which has a flat spectral response, it has a different effect to what you would see with your eye, which has a different spectral response,
Gotcha.
if that makes sense.
I'll jump in with one. So I must have put this into my calendar, and so I ended up getting some very specific advertisements before this meeting talking about the use of OD filters for the solar astronomy, and so suggesting a 16.6 stop OD filter for solar astronomy. Is that ballpark consistent with your commentary?
That was going to fix that.
Trying to remember, I think it's like OD 1000 is the
Oh,
eye safe.
gotcha. So ignore the advertisements on the internet. All thank you.
Buyer beware, indeed.
Buyer
Yes.
beware. And then
There should be I forget the ANSI standard. There's a standard that applies to um, solar filters.
Okay.
Like I don't know if you recall during the last couple of solar eclipses we had when everybody was selling solar glasses, eclipse glasses. And there was a lot of hullabaloo about some being sold on Amazon that were supposed to be eye safe, but when you got them, they had no certification that they met the ISO standard. So that's the kind of thing that you do need to look out for when you're talking about solar observing.
very good, thank you. And just one real quick one. You had mentioned using 45 filters in your one experiment, but do you have a broad estimate for your total number of filters in your collection?
I think I probably got up around 60, 65 for a while, but then I sold a bunch off. So I'm probably down around 40-ish right now.
Only 40.
Only 40. But I only used like 2 or 3 filters.
Wonderful, thank you.
Welcome.
So I have another question. So, and I'm not sure if it's even a good question, but I'm going to have to get my buddy Tom here to help me on it. I have a one-shot color camera, and I think it has an IR.
The camera itself has IR. In this is
Hold on a second. Let me.
Yeah, I can't quite hear him.
One second, we're passing the microphone.
We both have the same camera. It's the ASI 2600,
Mhm.
and the one-shot color version has built-in IR UV cut, and but the mono version does not. Right. So
Yes.
that's wide open, but yeah, it's pretty sharp cut off. right? So,
Yeah, I wouldn't be concerned about the performance of that UVR cut. ZWO knows what they're doing in that regard, so they would have put a nice, like all of the H alpha band is going to be there, and it's going to be nice sharp cutoffs.
Gotcha. And I have, I guess, one final comment to make. So my strategy so far has been, oh, that looks like a cool filter. I think I'll get it. And then, so I'm hoping I'm not going to wind up at 40 at some point. But then afterwards, I talked to my buddy Dave and said, hey, Dave, what did I buy this for? Oh, you didn't need that, Kevin. So I assume that's a bad strategy.
Yes, do not just buy every advertisement that you see, go and buy a filter.
Gotcha. Any more questions?
I got a question online.
Go ahead, Blaine.
Yeah, this is Blaine. I have a Hyperstar and I've been doing imaging. I do imaging with both OSC and monochrome ZWO cameras. And I have been using the moon and sky glow filters, the Optilong one with the OSC camera, and the beta version with the monochrome. And I guess my question is, well, probably two parts to this. One is maybe more than a comment, but if you have something to add to it, I've noticed that at least with the Moon and Sky Glow filter on the OSC camera, that it tends to, by happenstance, offset the double green sensitivity in the Bayer matrix.
Okay.
And I was wondering if you had any comment about that. And the other question I had, as far as the Hyperstar usage, if you had noted that there was any issue with the band shift for the Moon and Sky Glow filter affecting anything when using the Hyperstar.
So starting with your second part first, no. So I don't know if you can recall the spectrum that I had up on the screen there. Can you still, yeah, you can still see my screen, right? Let me go back to the graph of that filter. So as you can see, the bands are all quite wide, like on the order of 50 nanometers or like several hundred nanometers wide. So in that ballpark, bands that wide, the sensitivity to F ratio is negligible. So you probably wouldn't be able to observe any difference using it at F10 versus F2. In regards to your noticing that it is helping with the double green, so for people not understanding what is meant there, so well, all Bayer matrix cameras available nowadays, CMOS days was different, but nowadays CMOS cameras, the 4 pixel array is 2 greens, 1 red, and 1 blue. So in effect, the camera is twice as sensitive to the green channel. As a result, depending on the kinds of filter you use, you might end up with an image that's really green in appearance. I found this to be true of multi-narrowband filters when the O3 passband is wider than the hydrogen alpha passband. The early multi-narrowband filters to come out, they called them tri-band. They had H beta, O3 in one, and then H alpha. Because of that wide passband in the green area, combined with the 2 pixels green on the color camera, meant you got a white balance in your image that was really biased green. So it's an interesting observation that you've made. I wasn't aware that using the Moon and Sky Glow actually helps to compensate for that. So it is, you can kind of see from this plot, if green is in the 500 nanometer range, 500, 550, it is blocking a fair amount of light in that range. So that makes sense to me. that would be the case. So yeah, interesting observation. Thanks for bringing that up.
Okay, any final questions? Hey, Jim, that was fantastic. I tell you,
I see hands clapping, but I don't hear
as you can tell
anything. I
as you
just
can
see
tell
all
from
these silent hands.
as you could tell from my strategy, I certainly learned a lot more about filters than I knew yesterday. Although I did watch
great.
one of your videos early on, and this helped a lot. This kind of really kind of cleaned up my knowledge of it. So thanks so much, appreciate it. I know you're up in Canada, and is winter over yet?
Yes, finally we had a high today in the low 80s, so that's good. A good sign.
Nice, very nice, good. Well, thanks so much. Truly appreciate it. You're very kind, and one more time, round of applause.
All right. Thank you. You're all very welcome. Thanks for inviting me.
All righty.